Hello students, welcome to the course on Basic Electronics Engineering and the course code is EC101. This is the course for BTech second semester EC students and first semester CSE students. Myself, Dr. Shurojit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. In the last class, we have started insulator, semiconductor, introduction of insulator, semiconductor, and conductors. Then we have completed the concept of valence band, conduction band, Fermi level, Fermi energy level, temperature effect on Fermi energy level. Then mainly two types of semiconductors we already discussed in the last class. One is intrinsic semiconductor. That means it is a pure semiconductor where electron concentration in the conduction band is equal to the whole concentration in the valence band. Then we have completed extrinsic semiconductor. Extrinsic semiconductor means it is not a pure semiconductor. Some doping is added, and these extrinsic semiconductor are again two types. One is N-type semiconductor and other is P-type semiconductor. In case of N-type semiconductor, pentavalent element, that is group 5 in periodic table such as phosphorus, is introduced in silicon crystal, and in case of P-type semiconductor, group 3 element in periodic table such as boron is introduced as a substantial impurity in tetravalent silicon. And in case of N-type semiconductor, the Fermi energy level is near the conduction band, and in case of P-type semiconductor, the Fermi energy level is near the valence band. So these are already we discussed in the last class. So let us start lecture number 2 from the module 1, that is basics of semiconductor. And the today's topic for the discussion is drift and diffusion current, mass action law, charge neutrality in semiconductor, Einstein relation in semiconductor, and few numerical problems based on drift and diffusion and Fermi energy level. And the lesson objective of this topic is study the basic properties of semiconductors, including the band gap, charge carrier concentration, doping, and charge carrier injection or excitation. And this topic is mapped with CO number 1. So let us start lecture number 2 from the first module, basics of semiconductor, with the topic of drift and diffusion current and mass action law. So first we discuss on mass action law or law of mass action. What is mass action law? At a given temperature in thermal equilibrium, the product of electron and hole concentration is always a constant and equal to the square of intrinsic carrier concentration. That means product of electron concentration and hole concentration denoted as say N0 and P0 equal to Ni square, where N0 and P0 are equilibrium electron and hole concentration respectively, and Ni is the intrinsic carrier concentration. The equilibrium electron and hole concentration are given by the following expression. Say N0 is equal to Ni into e to the power EF minus EFI by KT, and P0 is equal to Ni into E exponential minus of EF Fermi energy level minus EFI by KT, where EF is the Fermi energy level of doped semiconductor. So, an EFI is the intrinsic Fermi level. K is the Boltzmann constant and T is the temperature. Now, laws of mass action can be arrived easily by taking the product of the above expression. Now, Fermi level changes from intrinsic Fermi level when donors and acceptors are present. For N-type semiconductor, obviously N0 greater than Ni and P0 less than Ni. Thus, EF greater than EFI and N0 greater than P0. Similarly, in a P-type semiconductor, P0 greater than Ni and N0 less than Ni. So, EF obviously less than EFI and P0 less than N0. So, this is the mass action law. Next is the drift and mobility of charge carriers. What is drift? The free electrons and holes move randomly in a say a chaotic manner in a semiconductor at any particular temperature due to thermal agitation. See in the figure, these free electrons can move in random manner or chaotic manner. Now these free charge carriers moving in a given direction suffer collision with the fixed ions and change their direction. The average distance between two successive collisions is called mean free path. Now, owing to random nature of collisions, the number of electrons crossing a given cross section at a given time in a particular direction is the same as those moving in opposite direction. So the net current flowing through the semiconductor is zero. Now, if an electric field is applied to a semiconductor, electrons and holes will be accelerated in opposite direction due to the force exerted on them by the field. Now the electrons would be accelerated in a direction opposite to the direction of electric field, the velocity of the electron would increase with time, but not continuously due to collisions with the fixed ions. The electrons will lose energy during collision, and in the steady state, their velocity will attain a finite value. The regular motion of electrons or holes in a particular direction in an electric field is called actually drift motion. And the steady value attained by the charge carriers in drift motion after certain time is basically called drift velocity. The net drift of charge carriers gives rise to a drift current. The drift velocity of charge carriers in a semiconductor is proportional to the applied electric field for low values of field. Therefore, drift velocity is denoted as Vd, which is proportional to the applied electric field. Therefore, Vd is equal to mu into E. This is a very, very crucial expression, where mu is called the constant of proportionality. Basically, it is a low field mobility, which is the drift velocity per unit electric field. Therefore, the unit of mobility mu in a SI system is meter square per volt per second. Mobility means the ease with which electrons or holes drift in the material. So basically, drift is due to the applied electric field. Next is the diffusion. Drift current density. Before going to the drift current density, let us consider a cross section of a semiconductor of area say A, whose length is L, and which the electrons drift due to the application of electric field. And the area of the cross section or volume of the cross section is basically A cross L. If A is the area and L is the length, therefore the volume of the cross section is A into L. Now let N, capital N, be the number of electrons and time taken by the electrons to cross the distance L is say T. Then the current density in positive X direction due to the drift of electron only is denoted as say J in X drift, which is say rho into EX, X direction electric field, which is basically N E mu N into EX. Okay. Now, the current density, similarly, the current density in the positive X direction due to hole drift is JPX, denoted as JPX drift, equal to PE mu P into Ex, where P is the whole concentration and mu P is the whole mobility. Therefore, the total current density due to the drift of both electrons and holes, Jx drift equal to Jnx plus Jpx drift equal to Ne mu n into Ex plus Pe mu P into Ex, which is say Ne mu n plus Pe mu P into Ex equal to sigma or rho into Ex. Therefore, the conductivity due to both type of carriers, which is denoted as sigma, equal to that part is Ne mu n plus Pe mu P. So this is the conductivity due to both type of carriers, both electrons and holes. Okay. Next is the diffusion. Another phenomena is present where electric field, external electric field doesn't require, which is called diffusion, diffusion of carriers. So apart from drift of carriers in an electric field, another transport phenomenon occurs in a semiconductor in the absence of electric field, where there is a concentration gradient of mobile carriers due to which the carriers move from the high concentration region to low concentration region. This phenomena is called diffusion, which is random motion of charge carriers. As in drift motion, the diffusion also, the carriers undergo collision with various scattering centers due to their random motion. Let the mean free path be L and mean collision time say tau. Since the collisions are random, the probability of movement in any direction is same as that in the opposite direction. So in this figure, this is the electron concentration profile nxt, which is shown at a particular time say t. The flux of electrons, flux means number of electrons crossing unit area in unit time normal to the area across a plane at say x0 at a time t can be obtained by taking two regions, say which is labeled as say 1 and 2 on either side of the plane x0, separated by mean free path L to each side. Let the electron concentrations in regions 1 and 2 be N1 and N2, where N1 greater than N2. the electrons move randomly in both regions. So on the average, half of the electrons in region 1 will move across x equal to x0 to the right, and half in region 2 will move across x equal to x0 to the left in a mean free time, say tau. Therefore, the net flux of electrons to the right of x0, say net flux of electrons to the right side of x0 is say phi n xt, because it is a function of x and t, which is say n1 minus n2 by 2 tau into L. Now again, n1 minus n2 is almost equal to actually minus dn dx into L. Why there is a minus sign present? Now minus sign is due to the fact that electron concentration decreases in positive x direction. Therefore, phi n xt equal to minus L square by 2 tau, just putting the value n1 minus n2 equal to minus dn dx into L in this first equation. And after putting this, we can get phi n xt equal to minus L square dnx t by dx. So which is basically minus dn, capital Dn, dnxt by dx. Or dn basically we have assumed here L square by 2 tau, which is known actually diffusion coefficient of electrons, which depends on collision parameters L and tau. Similarly, the net flux of holes due to hole concentration gradient can be obtained and is given by phi p xt equal to minus dp into dp xt by dx, where dp is the diffusion coefficient of hole. A current flows in a semiconductor due to diffusion process in absence, basically in absence of an electric field, and the diffusion current density can be obtained by multiplying the particle flux by charge. So therefore, the diffusion current density Jx diff, which is denoted as Jx diff. So it is basically the summation of Jnx diff plus Jpx diff. So which is E dn dn dx minus E dp dp dx. So this is very important expression for diffusion current density. That is Jx diff is equal to E dn dn dx minus E dp dp dx. So now we want to calculate the net current due to both drift and diffusion. In many semiconductors, the electrons and holes move by both drift and diffusion in the presence of both the electric field and carrier concentration gradient. Thus, the total electron and hole current density due to drift and diffusion is given by the following expression. Jnx is equal to Jnx drift plus Jnx diffusion, which is n e mu n ex plus e dn into dnx by dx, and jpx is basically jpx drift plus jpx diffusion, so which is pe mu p ex minus e dp dpx by dx. So this is the total current, total electron and hole current density due to both drift and diffusion. Now there is a fantastic relation between diffusion coefficient and mobility. And this relation is basically called a famous relation which is called Einstein relation. Now, in Einstein relation, what does it says? Diffusion coefficient, say D, is interrelated with mobility mu, is given by through Einstein relation is D by mu equal to kBT by E, where T is the temperature in degree Kelvin. Now diffusion is a random, irregular and disorderly motion in which entropy of the system increases, while drift is a directed, regular and orderly motion in which entropy decreases. Thus the ratio of D to mu signifies the ratio of disordered to ordered motion. It is an important, very important relation. Thus basically D by mu is basically the proportional of proportionate of kb into T. So what is kb into T? It basically produces basically the energy, thermal energy. Since kBT is the thermal energy which produces disorderly motion of the charge carriers. So this is all about drift, diffusion and Einstein relation. Drift current density, diffusion current density, and the relation between diffusion coefficient and mobility. That's all about. Now I move for a numerical problems based on the Fermi energy level. What is the problem? The problem is like that. Calculate the probability that an energy level 2 kT above the Fermi level is occupied by an electron at T equal to 300 Kelvin. Again, I am repeating the problem. Calculate the probability that an energy level 2 kT above the Fermi level is occupied by an electron at 300 Kelvin. What does its solution? It's simple mathematics. This type of problems comes in semester. The probability of occupation of an energy level by electron is given by the Fermi Dirac distribution function. So from this expression, Fermi Dirac distribution function, you can easily solve the problem. Where if E is equal to 1 by 1 plus exponential E minus EF by KT. So it is 1 plus exponential E minus EF, that is 2 KT already given by KT. So it is e to the power exponential power 2. So it is 0.1192, that is 11.92%. And the next problem, based on the intrinsic intrinsic conductivity or intrinsic resistivity, like that is basically from drift current density. Again, this type of problems are very usually comes in semester examination. Find out the intrinsic resistivity of germanium at 300 Kelvin if the intrinsic carrier concentration of germanium at 300 Kelvin be 2.33 into 10 to the power 19 per meter cube, where mu n and mu p are given, where mu n is equal to 0.39 meter square per volt second and mu p is equal to 0.19 meter square per volt second. Therefore, the intrinsic conductivity of germanium is, say, sigma I, which is already we know that it is E N I into mu n plus mu p, and the electron charge is already we know that 1.6 into 10 to the power minus 19, and Ni is given, it is 2.33 into 10 to the power 19, and mu n and mu p both are also given, that is 0.39 and 0.19 meter square per volt second. So it is 2.16 Siemens per meter. Therefore, what is intrinsic resistivity? Just the inverse of intrinsic conductivity. So it is 1 by 2.16, it is 0.46. So this type of problem normally comes in the examinations. So that's all about semiconductor physics. Okay. Thank you all. So now I am ending the today's session. Thank you.